Alright, so for those of you that in class, I'm going to have to do a recap of the notes because I didn't have the audio up on the lecture. And so this is the notes. Might have a little more detail that I didn't have in the earlier lecture, and hopefully it'll be worthwhile. So the first question I really ask is, why do we do mathematics? And mathematics is an old way of thinking that human beings have developed. It's a set of tools. And some of the first things that are known as mathematics is in the Ishigo bone, I think, which is a bone that's marked with notches, and the notches are grouped into groupings of 13 groupings of 28. And so they look like they're counting lunar calendars. And literally, astrology, astronomy, hunter-gatherers needed to know time. We live in a world where we have calendars, but those calendars had to get invented. We had to measure them out, and it was a complex process. Watching the days change, watching the sun change, watching the stars change, and all those calendars came together to give timekeeping. The power of astrology was the fact that looking at the stars could predict when the crops would grow. So why couldn't it predict, who would be king or who wouldn't be king? But it was this predictive power. Predictive power found in quantity. Now, mathematics itself is a language that forms in the brain's patterns. When we anthropologists study primitive cultures, and I'll put primitives in quotes because we live in a culture that we might think we're complex, but we still cause a lot of suffering. So primitive, technologically advanced, what do we mean by it? It is a very relative thing. But and this shows up in like Dungeons and Dragons, where orcs, right? Orcs, you'll sometimes see in some of the books go 1, 2, too many, because that's their counting, because they have a limited intelligence, or at least number sense. But they've noticed that tribal hunter-gathering societies that still exist have a counting system that isn't as complex as the one that we have, and it's 1 through 5, 6 or so, and then they have many and very many as concepts. But you could say you would catch 11 or 15 monkeys in one of the tribes, one of their main preys that they hunt, but they wouldn't know the difference. They wouldn't have a way of articulating it. Without the words and the concepts for talking about things, we have a very hard communication time, plus the hard time of coming up with the mental difference. And so what we think happened is you want to build, a jacket. And you go from 11 to 15 of your prey being many to you need 14 pelts of an adult rabbit, right? And so now you start to need to count. You get recipes. And it's this predictive power, this recipe that comes from quantity, that we as human beings learned. We learned how to take the number of things, and use it to predict. And in that, we start coming up with the idea of the language of mathematics and how counting can progress to where we model reality. And a large portion of this course is going to be modeling with differential equations. Now, a differential equation is an equation that uses derivatives. of an unknown function. And what derivatives relate to is they are rates of change. Now, initially, in 1666, Newton invented, along with some work by Leibniz a little bit later, which gives us some better notation, invented calculus. But he invented calculus to solve dynamical problems, motion that changed with time. And you see this in physics. In physics you have kinematics, which is the study of motion itself, statics, things in equilibrium, and dynamics, things that are changing. And dynamics is what Newton was interested in. And to be honest, he invented the physics and the calculus we use now. And he was very successful in solving the problem of planetary motions and getting equations of motion. And when we mean solving, we mean that you take this system and you get one function, theta of t equals, and there's some motion that this goes through, but this has a circular motion, and so we would get that theta of t has some time dependency on it, and you could talk about, let's see, theta of t equals theta dot times d. And so there's some rate of change that theta dot comes across, and you'll see dot notation means this changing in time. And Newton was able to solve this, and you would get one equation that could describe the motion of one body if you had two bodies. But if he added the moon of this object in, so you had this rotation and this rotation, he found this could not be solved. Well, I shouldn't say he didn't say it could not be solved. He could not find an analytical solution where you could describe the motion of the moon that it made in all of space around this in one equation from these. And so the three-body problem, Newton could not solve. Later, Poincare actually proved that the three-body problem was unsolvable. Right? In like the late 1800s, Poincare proved it was unsolvable. And I think 3 or 4 years ago, we actually found that there is one three-body problem we can solve. We have three equal masses, equidistant from each other, rotate given the same motion in a plane. That is a three-body problem that can be solved into one function, where you're going to theta of t equals theta dot. And that's what we mean by solving. One equation or an equation comes out, it's solvable. And so these systems that we study might not be solvable. What we're going to find is that we might be able to solve them, but we should be able to find predictive answers out of them. One of the weird things is we don't always see it from coming out. And so we're going to explicitly find solutions where some differential equation will solve into, since the unknown variable is y of x equals, some relationship. So I'll put it as a big f, like some big function. And that's an explicit, we'll find a path down to it. We might find it implicitly, where dy dx plus exy equals some driving function. And we'll find that this solves, that we might be able to solve directly for dy dx, but not y itself. Or we might find, in one of the cases that come up a lot, that we can find an inverse function of y of x in terms of y and x. We'll get things like this happen a lot, especially with trigonometric identities and intervals. Or numerically. slash graphically, where we have some differential equation where dy dx equals some function of x and y, and we can graph it. We can graph what the differential equation is going to look like, but we might not get a solution for it analytically. But then with this graph, we can say, well, if I start here, all these derivatives say I'm going to have a solution that looks like this. And I can make a predictive numerical function with it. And so what we are studying are all the different types of linear, nonlinear differential equations that we can see, and the different techniques we're going to need to solve or to predict. We want to predict the future using mathematics, and so we're going to use all the tools to do this. And this is where the poetry language came out. We're taking calculus as a language and we're using it to describe reality. And that's what modeling is. And you'll see I'll work on models as we come through and the term modeling in a little more detail. Alright, so this is the first part. I'm going to stop this video here and I'm going to continue and chunk out kind of the lecture notes I had for lecture 1.